So to start off this lesson, we're going to continue talking about factors that affect solubility. And the first factor that we're going to look at is pressure and how pressure affects the solubility. We're going to be looking at gases because pressure actually doesn't affect the solubility of liquids or solids. It simply affects the solubility of gases. So the solubility of a gas in any solvent is going to be increased as the pressure above the solvent increases. So this figure is going to help us to understand that the gas molecules that you see right there, those are carbon dioxide molecules. And so what this is showing you, the left-hand side diagram shows you that the rate of carbon dioxide molecules leaving the water equals the rate of carbon dioxide molecules dissolving into the water, and therefore you are in equilibrium because the rate of one process equals the rate of the opposite process. Now, if you decrease the volume, which happens in the middle diagram, what happens is that the pressure above that liquid increases based on Boyle's law. And so what actually happens is that more carbon dioxide is going to be able to dissolve. Now the reason why is that when you increase pressure, the rate at which the gas molecules are going to be striking the liquid surface, that increases. And so that's actually going to increase the rate at which the molecules enter the solution. So increasing pressure increases the collisions of the gas molecules with the liquid, therefore increasing the solubility of the gas in the liquid. Now, a way of representing this, if you can see on this graph right here, you can see as partial pressure increases, the solubility of all four of these gases also increases. So there's actually a law to help describe this characteristic of gases, and that's Henry's law. So Henry's law states that the solubility of the gas equals the Henry's constant times the partial pressure of the gas. So Sg is the solubility of the gas in the solvent. Pg, that's the partial pressure of the gas that's over the solution, which in the diagram above, in the figure above, is increased by decreasing volume. And finally, K is your Henry's law constant. Now, notice that what this is saying, based on what we've already learned from gas laws, is that solubility of a gas is directly proportional to the partial pressure of the gas over the solution. So that's the first factor that we're going to study in this lesson. The next is temperature. So the solubility of a solid increases when you increase the temperature of the solution, and that makes sense because if I'm wanting to dissolve, let's say, hot cocoa powder into water, I want the water to be as hot as possible to maximize the amount of solid that dissolves into the liquid. And you can actually see this with a graph. So the figure on the left-hand side, that graph shows you ionic compounds and their solubility, which is measured in grams of that ionic compound per gram, 100 grams of water. It actually increases as you increase the temperature. For the most part, there are always exceptions. Now, the solubility of gases actually decreases when you increase the temperature, and you can see that in the graph on the right-hand side. Now, one thing to keep in mind, we've been talking about solubility of gases. One example of solubility of gases that you experience on, hopefully not an everyday basis, but maybe every day, is with sodas. So the ideal conditions to drink a soda are under high pressure and low temperature. You want it to be as cold as possible so that you have as much carbon dioxide in the soda as possible. So the way that manufacturers facilitate this is that they pump the sugar water with carbon dioxide, and they don't just stop there. Instead, they continue to pump extra carbon dioxide into the bottle in order to maximize the partial pressure of carbon dioxide over the sugar water solution. The other thing that they do is they put the sodas into refrigerators to keep them as cold as possible. Once you open a bottle of soda, however, you've decreased the partial pressure over that liquid. That will decrease the solubility, which enables the carbon dioxide to escape. However, the best way to maintain a carbonated drink and keep it as fresh as possible is to keep it in the fridge. So if you do that, even though pressure is decreased, you'll be able to keep the carbonation for longer than if you have it at room temperature, because the solubility of the gas decreases when you increase temperature. So here's something that I want you to think about. Warm water is less dense than cold water, and so I want you to consider how temperature affects the solubility of gases and explain why this is an issue if water in a lake is extremely warm at the top layer, how that affects the aquatic life even if it's living in the cold water. Why is this an issue? And this actually leads to aquatic death. So think about it and write a quick explanation, and we'll talk about it in class. In this section, we're going to be talking about how to express the concentration of solutions, and we can do that qualitatively by talking about whether a solution is dilute, meaning it has a small concentration of solute, versus concentrated, meaning it has a large concentration of solute. So for example, if a drink that you are drinking is extremely concentrated, that means you have a lot of solute, while if it's extremely dilute, you have more water than you have solute. Now, that won't suffice for us. We have to also talk about solutions quantitatively. Now, there are 3 different ways of quantitatively expressing solution concentration that we'll talk about in this lecture. The first one is mass percent. So mass percent of a component is simply the mass of the component divided by the total mass of the solution. And then to get the proper percent, you just have to multiply by 100. So for example, if I say that my solution is a 5% concentrated solution of copper sulfate, let's say for example, what that tells me is I have 5 grams of copper sulfate for every 100 grams of my solution. The next way of quantitatively expressing solution is parts per million. So parts per million is extremely similar to mass percent, but instead of being for every 100 grams of solution, it's per every million grams of solution. So what you do is you take the mass of the component that you're interested in, you divide it by the total mass, but this time you multiply by 1,000,000. So if, for example, I say that water in the United States has a concentration of arsenic of 0.010 parts per million, what that tells me is that I have 0.010 grams of arsenic for every 1,000,000 grams of water. So parts per million is a quantitative way of expressing solutions that are extremely dilute, clearly. And the last one is molarity. Now molarity is one that we're going to be using quite a bit in the lab, and molarity is simply the number of moles of your solute divided by liters of solutions. The reason why it's so easy to use is because you simply have to measure the amount of solute on a scale, and then you create your solution by adding water to get a final volume of your entire solution. So let's look at some example problems right now. So there are actually 2 different ways of completing this problem. It tells you that you have a 250 milliliter solution of 0.347 molar glucose. And what you're doing is you're going to be adding more glucose to that. So the first way that you could complete this problem is by finding the new concentration, so that using 2.39 grams, finding what concentration this would produce by putting it into 250 milliliters of solution, and then simply adding the 2 new concentrations. Now, I'm actually going to do it a different way because it allows me to explain the concept of molarity and make sure you guys are clear on concentration and how to calculate molarity. So what I'm going to do actually is say, all right, well, if I have a 0.347 molar glucose solution and I have 250 mils of that, the first thing I want to calculate is how many moles of glucose I start with. And so my formula for molarity, if you'll remember, is that molarity equals your moles of solute divided by your liters, volume in liters of solution. Okay, so I'm going to plug in all of the values that I know for this problem. I know that my concentration, the molarity, is 0.347 molar. I don't know my number of moles of solute, so I'm going to just put that as X. And then I know that the volume of my solution is 250 milliliters. Keep in mind this needs to be in liters, so I'm going to divide that volume by 1,000 to get 0.25 liters. And now I can solve for my number of moles. So the number of moles I end up getting is 0.08, I'm going to say 7 moles because I want 2 significant figures. Okay, I got 0.08675 moles, so I'm going to round that to 0.087 moles. Now, that tells me how many moles I started with the solution. Now that I'm adding 2.39 grams, I can figure out how many moles of glucose that provides. Now, in order to determine moles, I have to write the formula for glucose, which is C6H12O6. So since I'm converting into moles, I need to put the molar mass on bottom of glucose, which is 180.156 grams, and I'm going to put the 1 mole on top. And so when I divide, what I end up finding is that the number of moles that I'm now adding to my solution is 0.0133 moles. Okay, so I now have this many moles and this many moles of glucose in my solution. So if I sum them together, I find out that I have exactly 0.100 moles. Alright, now it tells me that the volume of my solution stays the same, so I know that this is my total number of moles of my solute, of my glucose. Now I'm going to divide that by the volume of the solution, which stays is 0.25 liters. And so what I end up finding is that my new concentration is going to be 0.40 molar. Now if you did this the other way, by finding what the new concentration would be once you add the 2.39 grams, and then simply added the two concentrations together, you should also get 0.40 molar.